So our third and final speaker tonight is our very own MC Heisey, who will be telling us about fun with gravitational lensing, one of the most interesting things to come out of general relativity. Interesting fact about MC Heisey. She has seen Phantom of the Opera, the musical, live and in person more than 50 times. Some uncountable number larger than 50. So there you go. Take it away, MC.
To be fair, I used to live in London and I had to walk past the theatre every day. I'm only human, damn it. I also saw Lord of the Rings, the musical, 42 times in the space of a year, but let's not talk about that. So, just out of interest, how many of you were at the very first Astronomy on Tap ATX a year ago? I know you guys were. Okay, we have a few. So I gave a talk at the very first one, which was not on my research. It was an historical thing. So finally, after a year of running this thing, I actually get to talk about what I do, which is really exciting. So fun with gravitational lensing. This is a cool byproduct of the theory of general relativity. And it gives me a job, so I'm really in favor of it. So we've already heard a bit about what general relativity is. So let's have an illustration. We've got some flat space here, and anything, matter, light, moving along it moves in a straight line. If we introduce some mass into this space, the space gets curved, and now this object or light gets bent as it's going past it. So we're familiar with this mostly in terms of matter having its path curved. So this is why the Earth stays in orbit around the Sun stays in orbit around the center of the galaxy. But it also works for light. And this is really cool, because if you can imagine this yellow line here being a light ray, if I'm standing over here and I'm looking at whatever that light's coming from, I'm looking in this direction, and I think this object is over here. It's actually over here is where the lights really come from. So this is how the positions of objects appear to get distorted in the sky because of general relativity. So we've already heard earlier about how general relativity was tested. So I'm going to run through this pretty quickly. We have a bunch of stars. We can measure their positions. If we look at them when the sun is in the way, those positions are going to change. But of course, as we've already heard, you can't normally do that because the sun is really bright and you can't see stars the other side of the sun, unless you bring in the moon and cause a solar eclipse. I had a lot of fun with PowerPoint animations today. During a solar eclipse, you can actually see the stars that are on the other side of the sun, and so you can see that these positions are different than you would otherwise measure them. So this is the main test of general relativity. Einstein, when he first published GR, suggested that this would happen. It was finally tested in 1919 during a solar eclipse. Two teams went to one in Brazil and one to just off the west coast of Africa, and were able to measure positions of the Hyades cluster right behind the sun during the eclipse, and found, lo and behold, it moved. And we had this, as you've already heard, somewhat hyperbolic headline in the New York Times. And this is really what propelled Einstein to fame. He became an absolute celebrity after this. Within a year, there were something like 100 books written on the subject of general relativity. And so he obviously acquired an awful lot of fame and glory, not at all undeserved for this. Someone who really doesn't get any recognition is this guy. This is Fritz Zwicky. He's from Bulgaria, but worked at Caltech. One of his most famous quotes, he was somewhat irascible. He likes to say that astronomers were spherical bastards, because whichever way you look at them, they're still a bastard. He was really known for coming up with really outlandish theories, many of which didn't really work out, but many of which did. And one of the really amazing things that he came up with was this idea that if a star is going to deflect light as it travels past it, then nebulae, this is what they called galaxies at the time, which can be hundreds of billions of stars, should surely deflect the light even more. So this is just a little note in a tiny little letter that he wrote in 1937, saying that he suggests that nebulae offer much better chance of observation of these gravitational lens effects. This is the bending of light. He then went on to suggest that if we were to discover these images of distant galaxies that have been bent by more nearby galaxies, this would be a really cool thing. Not only is it a test for the general theory of relativity, but it would enable us to see nebulae, galaxies, at distances greater than those ordinarily reached. So that's what I'm going to talk about, why this is the case. Why would seeing galaxies whose light has been bent by foreground galaxies enable us to see further? And it's because this effect actually magnifies the distant image. So if we imagine here, we have the Whirlpool Galaxy sending its light down to us, which we're observing with the Hubble Space Telescope. The light goes off in all directions, and only that middle beam there gets to us. We put a big cluster of galaxies in the middle, and it acts kind of as a lens, hence the name gravitational lensing. It's focusing light towards us. So we actually get more of the light. We also see multiple images. You can see there's this one here that goes straight through the middle. But it can also go this side and get bent round. It can go the other side and get bent round. Of course, it's in 3 dimensions, so you can also imagine one like being above the screen and one below the screen. So you can get these configurations of multiple images of your galaxy. And this is really useful because if you have a galaxy that's multiply imaged, you're getting more light and maybe you're more likely to see it. So we're looking for things that are very, very far away. Being far away, they are obviously very faint. Also, the further away we look in the universe, the further back in time we look. And at the kind of level that I'm interested in, we're talking significantly far back into the history of the universe. So we're looking for galaxies that were forming right after the Big Bang, some of the very earliest galaxies. They're intrinsically small. So we're looking for things that are very small and faint, and they're extremely far away. So this effect could be really helpful if we can prove that it exists. So to give you an idea of what kind of configurations of images we might expect is a little demonstration you can do at home using a wine glass. I recommend you empty the wine glass first. And if you look at a small source of light, like a candle flame, if you line up your wine glass perfectly and look at it through the base of the glass, you'll see this perfect ring shape in the lower left. And this is what we call an Einstein ring. So the light from that little candle has been spread into this gigantic ring. Because of weird mathematical effects I won't go into, the surface brightness is exactly the same as the original candle flame, but it's now been spread into a much bigger area. So there's a lot more light there. It's also a lot bigger, so if there was any detail to see, you'll be able to see it a lot better. Of course, this only works because you have a nice symmetrical wine glass and it's perfectly aligned in front of your candle flame. The universe is never perfectly symmetrical or aligned. So we wouldn't necessarily expect to see something as perfect as that, or it might get close. So what we see more often is things that are slightly offset. So on the right-hand side, these are examples of where the glass is a little bit tilted or off-center from the candle flame. You get these characteristic arc shapes. So here you have an arc here consisting of 3 images, and there's another image there, and there'll be one behind the stem that we can't see. And on the lower one, you have 2 images, one either side, and then one in the center that's kind of blocked. So there's always an odd number of images if something's multiply imaged, but the one in the center can be demagnified or blocked by the thing that's doing the lensing, so you don't always see it. So depending on who you talk to, people will either say there's always an odd number or there's always an even number. They mean the same thing. It's just whether they count the one in the center. So this gives an idea of what we might see if this effect were real. But it's extremely difficult to see because these things are very, very far away. They're very faint. So it was completely hypothetical. This was published in 1937, Zwicky's idea. It went completely ignored for a really, really long time. The thing that changed everything was the development of the CCD. So until the mid-1980s, all astronomy was done on photographic plates. So you get an image that looks something like this. This is the Horsehead Nebula. Can anyone see the Horsehead Nebula? I'm looking at the amateur astronomers. If you can't see it, no one can. So it's right there. There's a slightly darker patch there. So these had very, very wide fields. They're also not very sensitive. So it's very difficult to see faint detail like this. So sometime before the 1980s, some experiments that were going on at Bell Labs into memory storage devices. So they were looking for ways you could store electrons and then read them out. And they found that it was kind of weirdly different depending on the light in the room at the time. And so they had unexpectedly invented a really, really sensitive light detector. And it was astronomers who pounced on that and said, that's amazing, we want that. And so they developed CCDs, charge-coupled devices, which we now call digital cameras. So this is an image of the same bit of sky, zoomed in a lot, taken in 1999, with the Canada-France-Hawaii telescope, which is in Hawaii. And the same object taken again in 2011 with an upgraded CCD. So we heard earlier about why you should care about pure research. This is an example of how astronomers latched onto a technology, and as a result, we all have cameras in our cell phones. So this has completely changed the world, but astronomers just wanted to see nebulae better. So we have these CCDs now. In 1985, one of the first pictures taken with the Canada-France-Hawaii telescope with its brand new CCD was this guy. This is Abell 370. It was published in 1986, and the observations were done the year before that. And do you see anything weird in this image? There's this thing here. This is known as the Dragon. It's a normal spiral galaxy. Looks a lot like our Milky Way. But it happens to be behind this cluster. All the other specks in this image are cluster galaxies. For anyone who hasn't seen me talk before, we tend to always show images as black on white. It saves printer ink. So what we have here is a cluster of galaxies. So all these blobs in this image are hundreds of billions of stars. And then this thing here is just one background galaxy whose light has been distorted because of the foreground cluster. So because we now have the Hubble Space Telescope, we have a much shinier image of this thing. So this, you can see now why we call it the Dragon. And you can kind of see with this level of detail, this is the spiral galaxy here. And one of these spiral arms has just been warped into this huge tail. So we actually have posters of this image available over on the info desk for free if you want to take one as you leave. So this was, as I said, published in 1986. This was the first proof that Zwicky was onto something. Clusters could be really, really good gravitational lenses. And the reason is that galaxy clusters, which can be thousands of galaxies, are the biggest gravitationally bound structures in the universe. So in 1997, this thing was discovered. The lower right is a fly-through. You're just flying around the cluster. And then the image on the left, you can see the thing highlighted with the square is a background galaxy whose light has been warped by this cluster. This has the very imaginative name of MS1358. Again, you should revoke our naming privileges. We suck at this. So in 1997, this galaxy here became the most distant object known in the universe. And it was the first time that anything other than a quasar, which was the brightest things in the universe, had held that record. And it's because of gravitational lensing, because this is a very small, faint galaxy that's been made visible because of this magnification effect. So that was 1997. The next massive game changer came in 2009. The last service mission, this is very sad, the last service mission to the Hubble Space Telescope, which installed Wide Field Camera 3, another incredibly boring name for something incredibly cool. This was an infrared camera that opened up a whole new area of science that we were able to do with the Hubble Space Telescope. One of its most famous images is this thing here. This is the Hubble Ultra Deep Field, which I have worn in the past. It's one of my favorite images. This is about a month of staring continuously at one tiny, tiny patch of space. So if you can imagine holding a penny out at arm's length, Lincoln's eye would completely cover that patch of sky. And it has 10,000 galaxies in it. So there's a couple of stars in this image. But basically, every speck you can see has hundreds of billions of stars in it. And it's so deep that we can see galaxies here as they were only a few 100 million years after the Big Bang. This is incredibly spectacular. And now the reason we needed infrared to do this, of course, we heard a few months ago from my boss, Steve Finkelstein, is that the light from these galaxies has been shifted redder because of the expansion of the universe. So if you look at the universe in optical light, all of the light from these very distant galaxies has fallen out of it. So they're going to be completely invisible until you get out to the infrared and they start to pop out. So what I work on now is we ask the question, what if you could do the Hubble Ultra Deep Field plus gravitational lensing? Wouldn't that be cool? So this is the Hubble Frontier Fields program. It's one of the largest programs ever undertaken by the Hubble Space Telescope. 840 orbits. An orbit is 97 minutes, so it's an awful lot of time. And it's looking at 6 gravitationally lensing clusters. So these are the positions of the clusters. They were chosen, they were known already, and they're known to be good gravitational lenses. They have lots of these arc shapes in them. And we wanted to get really, really deep imaging. So 1 and 2 down here are Abell 2744 and Max 0416. Honestly, these names. Max 0416 is in the Eridanus constellation. So anyone who hasn't seen me say this before know what else is in the Eridanus constellation? I'm looking at someone who should know. It's Vulcan. So that makes my nerd heart very happy. So those were the 2 first-year clusters, and they were completed last year. Just this summer, we got the 2 second-year clusters up in the north. These are Max 0717 and Max 1149. Which I'm going to show you images of later. They're so cool. So these were completed this summer. We're just starting to go through the data now. And then starting up pretty soon, we're going to have the final 2 clusters. These are Abell S1063 down here, and then on the equator, our very best friend, Abell 370, the Dragon. So we're finally going to get some really, really deep, amazing imaging of that cluster, which is very exciting. So what this program makes use of is the fact that the Hubble Space Telescope has multiple instruments, and you can use them simultaneously. So this is the footprint. This is the Hubble Space Telescope field of view, and it has many, many instruments, most of which I don't care about. The 2 that I'm interested in, Wide Field Camera 3, this is the one that was installed on that mission in 2009, and the Advanced Camera for Surveys down here. So you can observe with both of these, and you get images of 2 patches of sky a little bit apart. So here we're going to put Wide Field Camera 3 on our galaxy cluster. This will get us really deep infrared imaging of the cluster. And at the same time, we get an optical image of this random patch of blank sky just a little bit away. And then because of the way Hubble works, 6 months later, you can flip that over and take the optical imaging in the cluster and the infrared imaging in the blank bit of sky. So not only are we getting our ultra-deep field plus gravitational lensing in our clusters, we, for free, are getting a bunch of new ultra-deep fields in these random blank bits of sky, which is enabling us to find lots more of these very distant galaxies. So to give you an idea of what we might be looking for, let's imagine we take the Whirlpool Galaxy and put it behind our first cluster, Abell 2744. It's popped all the way over here because of this distortion. We're then moving it behind the cluster at trillions of times the speed of light, and we get all of these multiple images until it comes out the other side. Isn't that cool? All right, let's play that again. So I should tell you that I cheated when I made this. I mean, it wouldn't look quite this bright, but I wanted to make sure you could see it. It is moving, as I said, trillions of times the speed of light, and it's when it gets right behind here that it goes mad. So these are the kinds of things we're looking for. And when we finally got these images in last summer, they look like this. This is Abell 2744. This was our first frontier fields cluster, and the first papers came out within a week or so of this data being released. Lots of people went to work on it really, really quickly. That was not mine. I like to do things properly. So you can, all of the kind of big orangey things you can see in this image are cluster galaxies. There are people who care about cluster galaxies. I'm not one of them. So all of the other colored things, so mostly blue, are going to be background distant galaxies, and this is what I care about. Although, to be honest, anything you can actually see in this image is way too close for me to be interested in it. So just to see if you can take pity on me, I thought I'd show you some of my actual galaxies. So this guy up here, this is the kind of thing I look at all day. I look at blobs for a living. It's pretty depressing. But this is a really exciting blob. This is so far away that we're seeing it when the universe was only a few 100 million years old. This is actually looking 95% of the way back to the Big Bang, which is pretty amazing. So it's small because it's only just starting to form, and it's really far away. And there's another one up here. So this is a really cool thing that we discovered in this cluster, and there's another one. There seems to be a huge abundance of like really bright, this is bright, by the way. I don't often see things that are this good. This huge group of these galaxies that are 95% of the way back to the Big Bang in this top corner of this image. So just completely by chance, we took a picture of this cluster and we found what seems to be a cluster forming right in the early universe, which is really, really cool. So moving quickly on to our second cluster, this is MAX 0416. You can see some really cool gravitationally lensed arcs here. There's one at the top there. But as I said, anything you can actually see here is like really nearby. We're talking only 50, 75, 80% of the way back to the Big Bang. That's not interesting. So let's see something that's, the previous galaxies I showed you were 95% of the way back to the Big Bang. This one is 96%. And it's this orange blob in the middle. Can you see it? But there is a brighter one as well. This is 96% of the way back to the Big Bang. And this one here, which actually looks a little bit extended, is also 96% of the way to the Big Bang. So this is really exciting. This is showing us galaxies in the early stages of formation in the early universe. And these, normally, when you look at these things, like in the ultra-deep field, they might look like tiny blobs, but they're actually the brightest galaxies around at that time. Whereas these, because they've been magnified, are actually really normal galaxies. They might turn into, say, a Milky Way. And this is telling us an awful lot more about how galaxies and the universe evolved than just looking at the very brightest extreme things ever would. So I just want to finish with the most recent cluster, which is this one. Sorry, that was MAX 0717. I don't have time for that. MAX 1149 is really, really, really cool. This cluster features in 2 chapters of my PhD thesis, thanks to this guy here. This is a spiral galaxy. If you squint, you can believe it's a spiral galaxy, right? You can actually see spiral arms, and there's a little like bulge in the middle, exactly what you'd expect to see. Except this is more than halfway back to the Big Bang. This is really, really far away. It just so happens that in this particular cluster, the way the magnification works, it's not being stretched into an arc, it's actually being stretched in both directions. So it's literally just like using zoom on your computer. So we've just enlarged the image of this galaxy, which is really cool. It's also multiply imaged. So you can see this image here is the biggest one. It's got the main galaxy here, and then one of the spiral arms kind of wraps around this cluster galaxy here, which is giving it a secondary lensing effect. There's another image of the same galaxy right here, and another one up here. These are all the same galaxy that we're seeing 3 times. So completely by chance, it just so happened that when we went back to take the most recent imaging for this cluster, so it's the one before the most recent imaging, we saw something really weird that wasn't there before. These 4 dots, you can see 3 of them really clearly, And there's, if you really, really squint, there's a fourth one down here. These are a supernova that just happened to go off in this galaxy at the time that we took these images. This was not at all expected. You would never design a supernova survey the way the survey was designed. But I don't work on supernovae. MC Superdupernova does, so you can ask him if this is true. I was talking to the guy who's leading the supernova work in this program, and I said, you know, you keep telling us that this is really unusual and we got really lucky, but this is the coolest thing they found. But they found something weird and cool in every cluster that we've looked at, which to me says that's not luck. There is so much more of this really cool stuff than we ever believed there was. So what's really exciting about this is we have 4 images of this supernova. So this gives us a really good constraint on our lens model, because we have to work out where the mass is distributed so we know where all the multiple images appear, and we have to be able to reproduce that same bit of this spiral arm in those 4 places. But the light also takes different amounts of time to get to the different multiple images. So we saw this image here in 2014. This one here we think happened in 1995, so sadly it's too late to see that. But this one here could be any time between 2015 and 2020, depending on whose lens model you believe. And a lot of people have been putting more work into this recently, and they've got it down to, they think, like March to June next year, they're expecting to see this. Although my suspicion is they're saying that to get telescope time, and then they'll go, oh no, we're wrong, it's going to be like August to September, and it will just go on like that. But we will see next summer if we are correct. Thank you very much for listening to me talk about gravitational lensing.
All right, we got time for a few questions for MC Heisey right here.
When you use the model with the wine glass and you set it straight on the light, the light of the origin, how does that diminish when you're looking at it at the end? Or does it matter?
Okay, the question was, when I showed the demonstration with the wine glass, and I said, I was talking about the conservation of surface brightness, right? So you see the perfectly aligned one with the Einstein ring, and then the ones at the angle, you see a bit less light. So the surface brightness is always the same. Same with the offset ones. The amount of light per unit area always looks the same. The thing when you have it perfectly aligned enough to get the Einstein ring is that more of that light is being focused towards you. So you get this huge ring. So you've got that same surface brightness, but over a much bigger area, and hence more light than you do if it's a bit offset.
Second row here.
Why is there so much variation in color in these galaxies, all about the same age?
Okay, so the question is, why is there so much variation in color between these galaxies that are all the same age? That could be an entire talk in itself. The short answer is old stars look red and young stars look blue. So if there's a lot of star formation going on, they look bluer. There are different processes that can change the amount of star formation going on. So if you have galaxies merging, you're going to get a massive burst of star formation. It will make them look very blue. Galaxies that are in clusters tend to be older, and they get redder as the star formation dies off. But yeah, we could do an entire talk on that.
All right, one more question right upstairs there in the front row upstairs.
So one of these galaxies that are 95% of the way back, if you were in one of them looking outward, what do you see?
Okay, so these galaxies are like 95% of the way back to the Big Bang. If you're in one of those galaxies and you look out, what would you see? So do you mean if you're in that galaxy at that time, or in that galaxy today? Today. So if you're in that galaxy today, you would see basically what we see. One of our principles of cosmology is that wherever you go in the universe and whichever direction you look, everything looks the same. So they could look out and see us, they could see the Milky Way, but they would see us as we were 95% of the way back to the Big Bang.
All right, it's time to.
Okay, all right, we need to wrap up. So thank you again.